So, let us now move on from there and say, all right, if I can't do ILP, what is done in practice? What are the other techniques that I could use in reality, right? And one of the most popular is a technique that is called list scheduling. Sometimes it is also called priority list based scheduling or some other variant of this, right. The priority list based scheduling is the more accurate name. List scheduling is just a sort of contraction of that form, right. Effectively what it is saying is, I am just going to prepare a list of operations that are ready to execute at any given point in time, order them according to some priority, pick them out as and when I want, as and when something is ready to execute them, and let them run. The best way to illustrate this is to sort of use an example. So, I am going to schedule the differential equation task graph under a constraint of 3 processors, right, where I will assume that the processors themselves are homogeneous, which means that multiplication, addition, subtraction, comparison can all be done on the same processor with unit delay. Okay. So, the way that I would go about doing this is, I create something called a ready list and I maintain time, right. So, I have time 1, 2, 3, 4, 5 etc., and at any given point in time I am going to maintain which are all the operations that are ready to execute and decide which of them are going to execute on my hardware. Okay. In terms of this, I can then go to the graph and basically look at the ones that have no dependencies. What are all the operations? 1, 2, 6, 8 and 10. None of them have any dependencies within this iteration to start with. So, I can put all of them into the ready list right at the start. Now, what I need to do is pick some of them and schedule them for execution in time step 1. Now, just for illustration, I am going to intentionally choose them in a not so good order, right, and I am basically going to say I am going to pick these 3 and schedule them. The point I am trying to make is, in principle you could pick any of the ready items in order to schedule, right. You might feel that the priority based on the critical path or something else is the most important one and that is what needs to be satisfied, but in reality that may also not be the one which is always optimal. Okay. So, if I did not have such a priority list and all I had was that everything that is ready has the same priority, I could have picked 6, 8 and 10 as the operations to be scheduled. What that implies is that 6, 8 and 10 will get executed in time step 1. Now, what is the ready list in time step 2? 1 and 2 remain there. Okay. Because 6 has executed in step 1, now 7 is ready. Because 8 has executed, 9 is ready. Because 10 has executed, 11 is ready. Once again, nothing really preventing me from picking these. So, I would then end up with 7, 9 and 11 over here, right. What happens after that? It turns out that now I am stuck with only 1 and 2 being ready, because nothing new came out of 7, 9 and 11 being executed. Okay. Schedule both of them, and what I get is 1 over here, 2 over here. It does not matter whether I put it on P1 or P2 or P3, but after they are done, 3 will be ready. Execute that, 4 will be ready in the next step, and finally 5 will be ready over here. The good thing about this algorithm, by algorithm I mean the sequence of steps to be followed for solving the problem, is that it is very simple to describe and very simple to implement. all that I need to do is have some kind of a set data structure which keeps track of what are all the ready items, okay, and I need to pick as many of them as there are free processors at that given point in time and schedule them, okay. If I had a situation where some processors take more than one clock cycle to finish, that is also easy. When I go on to the next time step, I just keep track of the processors also, are they busy or are they free, and just keep track of how many operations are ready, how many processors are free to start a new operation, and just pick and choose and push them over there, right. Obviously, this was not a very good schedule, but fixing it is also, in this case at least, very trivial. I could have just changed it around and said, if I chose another scheduling set, then I would have ended up with something like this. In step 1, I would have got 1, 2 and 6, right, and okay, I need to get the ready list over here. So, to start with 1, 2, 6, 8, 10 would be ready. Let me switch back to black itself. So, what I would do in this case is that I would pick these 3 and put them here, right. In the next time step, what I would have is 8 and 10 are ready, but in addition to that, because 1 and 2 have executed, 3 also becomes ready, and because 6 has executed, 7 also becomes ready. Once again, keeping the critical path etc. in mind, probably what I should do is pick these 3 and 7, at least I need to make sure get scheduled, because those are the ones that have other things depending on them. So, I would then say 3, 7, 10, right. Where does that leave my ready list? 8 still remains on the ready list, because 3 has completed, 4 now comes into the picture, because 10 has executed, 11 now comes into the picture. All 3 of them can be scheduled, and what I will end up with is 8, 4 and 11 over here. And once I have done that, in time step 4, what are the ones that are going to be ready? Because 8 executed, 9 will now be on the list, because 4 executed, 5 will now be on the list, right. Remember that 5 had 2 things that it depended on, right. 5 depended on 4 and 7. So, just when 7 alone executed was not enough to put 5 onto the ready list, only after 4 also executed does 5 go onto the ready list. And in this case, finally what we have is, in time step 4, I will end up with 9 and 5, and the whole thing basically completing within 4 time steps, whereas this original one took 6 time steps. So, what you can see over here is creating this list and using it in order to schedule is a fairly simple and straightforward process. How you create that priority, that is, how do you decide which operation that is on the ready list is important and should go next, will ultimately determine how good your scheduling becomes. Okay. Once again, the example that I have given over here is for the specific case of resource constrained minimum latency, right, because I basically told you that there are 3 processors. So, there is a resource constraint, and then asking you to minimize the latency. Okay. If I wanted to do the opposite, which was latency constrained and then minimum resource, that is slightly more tricky, because basically what I will have to end up doing is sort of try with a given set of resources, see whether I am able to meet the time latency constraint. If I can't, then maybe I have to change that latency constraint or change the number of resources, right, until eventually I am able to schedule everything within the resource latency constraint that I need. Okay. But there are heuristics that do that as well. So, the actual compilers that we will be using later actually make use of these kind of techniques, right, in order to decide what operation goes into which scheduling step, right. But we are not going to be looking into the details of how they work. There are a lot of other sort of details that also come into this, right. In particular, there is one thing that can be done in certain situations, which is, depending on the type of hardware that you have, you might have a situation where you can actually chain operations together. And operation chaining essentially means, let us say that you had operation 8 and 9, there was a multiplication followed by an addition. If I instead had one hardware unit that can do a MAC, multiply accumulate, I might be able to put both onto one hardware unit and finish both the multiplication and addition within a single clock cycle. Okay. That depends on the type of hardware that you have. So, the task graph by itself cannot tell you whether or not chaining is possible, it depends on the type of hardware that you have. The second thing that actually determines this is, even if you have the necessary hardware, will you be able to do it subject to the time constraint that you have, right. In other words, let us say that I want this entire thing to operate at a clock period of 20 nanoseconds, I might find that chaining two operations together into a single clock cycle is easy to do. But if I had to do it with a clock period of 2 nanoseconds, I might find that it is very hard to do, and I have to basically pipeline the multiplier and adder separately, and I can't chain two of them into a single clock cycle. Okay. This is something you can actually observe when you use Vivado HLS for synthesis. As you change the timing constraint, you will find that the hardware resource usage increases, the type of pipelining that it does changes. It basically tries to chain operations into a single clock cycle when possible, and if it can't, then it will put them, schedule them across multiple cycles, use up more hardware, more clock cycles, but still try and give you a correct result.